our introduction, guys, we're gonna to create an anatomic image, a sound pulse must travel to a reflector located in the body. Ultrasound, remember, we send out pulses, you know, and then those pulses go and hit a structure in the body, and then they bounce back to the transducer, right? We don't get a lot of reflections back, right? We only get like less than 1% of reflections back. So then we have to worry about our amplification and things of that nature, okay? But this right here, this with the range equation, again, this is our last physical property concerning ultrasound waves right here, this chapter right here, okay? So the travel time of this journey allows us to accurately position a reflector. Here, this is an example right here, based on, you know, this right here, that's how we're able to get this image. So these waves right here are coming out this transducer, they're hitting this reflector right there, boom, some of them are bouncing back. And that's how we're able to create these images at different depths. So the travel time, because the machine is already programmed to go through soft tissue, so it's assuming that sound is always traveling at 1540 meters per second, 1.54 millimeters per microsecond, 1.54 kilometers per second, or as you guys read this chapter, 154,000 centimeters per second, right? Or however variation you want to say that. Again, it's important to know our units, because I was taking some practice tests because I'm trying to get a bigger test bank, so you guys I can just, you know, give you guys more information. I don't want to just give you straight from the book all the time. I'm trying to give you, so I was taking some practice questions, and you know, they are going to ask you to convert from millimeters to micrometers. So, you know, always know how to do your conversions. If you don't know how to do your conversions, go back to our PowerPoint in chapter 1 and 2. Okay, or just come to me and we can talk about it. Yes, ma'am.
This means it says here, accurately position the reflector.
At a certain depth. That's how we know. That's because, like, that's why we get like artifacts. Sometimes like refraction. You know, we know about refraction. That's transmission with the bend, right? So if the sound waves or something that's refracted, like remember I said if you doing a biopsy and you stick a needle in there at an oblique angle, then that needle, because the speed is so vastly different than the soft tissue, because it's metal, right? Then that's going to cause a refraction of that on that image, and you can actually see that it looks like you're sticking a needle in, but then it may look like it's a little off to the side a little bit. So this is my liver right there. Good mark. That's my liver right there. Then I have my needle coming in, right? My needle right there. But then when it refracts at a certain depth, it may look like that. It may not be. Remember we talked about refraction not going to be in a straight line. So I'm drawing that for illustrative purpose. It may not be that large of a difference, but it's not going to come in a straight line. It's not going to transmit in that straight line. And so it's going to.
It's two different mediums, or just
exactly, because they're so vastly different. Okay. The propagation speed. Remember that's what refraction is based on: propagation speed and the oblique incidence. So the propagation speed of that needle to soft tissue is so vastly different. That's going to cause a refraction on top of the oblique incidence. Okay. So that's what I mean by positioning at the correct reflector, because if we send a pulse out and it hits a structure, let's say it goes from soft tissue to fat to soft tissue. It's all sound travels slower in the fat, right? So when it is traveling fast through the soft tissue, it hits the fat and then it slows down. So that slowing down effect, when that reflection bounces back, that fat may not be accurately represented in the right place. It may be, think about it, it slows it down. So that's going to cause our reflector to go back slower as well, right? So in that case, our fat may be placed deeper in the image because of the propagation speed of that fat. Okay? So this is what the range equation is talking about, being able to accurately position structures for exactly where they need to be, instead of, you know, having all these artifacts. Instead of having all these artifacts. I hope that was a good explanation. Okay. So we have the time of flight or go and return time, guys. Time of flight and go and return time, synonymous terms. Basically, that's the time that it takes the reflector to be sent from the ultrasound transducer, hit the structure or hit the reflector, and come back. Okay, that's what that is. Time of flight, the go and return time. The time, boom, it's the elapsed time from pulse creation to pulse reception. Okay, go and return, time of flight. Okay, ultrasound system determine reflective depth by measuring a pulse's time of flight with a very accurate stopwatch. Again, that's how it knows exactly where to put that liver at exactly at that particular depth that structure is. instead of, you know, having, you know, a liver, like with ultrasound, X-ray, you know, it's all the structures are overlapping. It's not about the timing. So instead of having a liver and then having that kidney right within the liver, it knows that kidney is posterior, and so when it hits that, it knows it takes more time for it to travel to the kidney and come back, because it's using the 13 microsecond rule, and we'll get to that in a second. Okay. But definitely, being able to accurately position reflectors where they need to be, based on the 13 microsecond rule, because the ultrasound machine assumes that sound is always traveling at.
Transmission time?
Huh?
Transmission time?
It's the go and return time. The go and return time, not just transmission time. Remember, transmission time, that's just post duration, right? It's just post duration. Okay, so this is just our illustration of the time of flight. If you have a deeper structure, such as this one right here, then our time of flight is going to be more, right? Remember, I was walking one time and I was walking to Mrs. Seal, boom, I can walk to her and I can come back a lot faster. I'm already back to my to the transducer. But if I walk all the way to the door, the second one, it takes me more time to walk over here and then come back over here, representing the deeper reflector, meaning that it's going to be placed. That's how we get our depth. It's going to be placed deeper on my depth chart, or on my my image. Okay. So the deeper the reflector, the longer the time of flight. Okay. The shorter or shallower the reflectors are in purple, the shorter the time of flight. Meaning it's going to travel there and back a lot faster. And then we're able to send out another pulse, right? Because the ultrasound machine is going to wait, it's going to listen for all those pulses to come back. Okay? It's not just going to continually send out pulses, because then we have those beams colliding, and then we won't get an image. Okay? So it's going to send a pulse out, wait on reflections to come back. We get reflections, boom, it's going to send another pulse. But that's all based on perfect timing. Like I just said, that is on the accurate timing of the 13 microsecond rule, or gauging the time of flight.
So you can give an example of this, like the first one is the superficial, right?
Absolutely. Absolutely.
Thyroid,
Blood vessels, testicles, what else we do superficial? Any kind of lipoma, mass, you know, anything you do superficial to the skin. Liver, pancreas, kidney, you know, structures like that are going to have a much longer go and return time, and also we're probably going to use a different transducer for both of those things. Okay. All right. So the time of flight, guys, is directly related to how deep an image is. Okay. So the deeper the structure, the higher the time of flight. Okay. Direct relationship. Okay? The deeper the structure like this, the time of flight goes up. The go and return time goes up. Okay. Just the opposite. The shorter the structure, the more superficial that structure is, the less of the time of flight. Okay? It takes less time to go a shorter distance or a shorter depth. Okay? Go there. All right. Time of flight, directly related to the image and depth. Directly related to the image and depth. Okay? So, ultrasound system, like I already said, they're programmed with the average speed of soft tissue as 1.54 millimeters per microsecond. All the different ways I told you how to gauge that number. Know that number, okay? Know that sound travels a mile a second. All right, so the depth of a reflector can be accurately calculated from the go and return time using the following equation, guys. Using this equation right here, we can accurately detect how deep a structure is. The reason, so our depth can be determined by, of course, sound traveling at the speed of 1.54 millimeters per microsecond, multiplied by the go and return time. Okay? Multiplied by the go and return time. However long it takes the sound to get there and come back, times the speed of sound, divided by 2. Because that's going to account for our transmission and our reception. That's why it's divided by 2. Okay? That's how we can determine how deep a structure is, because we're not, and when we're trying to determine how deep a structure is, we're not concerned about the time. We're concerned about how many centimeters deep that structure is in the body. Okay? So that's why it has to travel the same the amount of time it's going to take to get there. We're going to take that amount of time to come back. Okay? That's why we're going to divide it by 2.
So the body question, no,
TOF, remember I said that's another word for go and return time. That's a good you pointed that out. Time of flight and go and return time are synonymous terms. Okay? time of flight and go and return time are synonymous time. So, no, that's actually perfect. All right. So, this brings us to our 13 microsecond rule right here, guys. 13 microsecond rule applies when sound is traveling through soft tissue. When we're diagnostic ultrasound technologists, so we always our main objective is to do soft tissue exams. That's what ultrasound is good at looking at, is seeing soft tissue. Okay, so that's why we're able to accurately see that liver mass, because of course the propagation speed between fat or whatever the mass is made of is different than the rest of the liver. So that's how we're able to accurately determine the shape of that liver, the depth of that mass, because of the reflections we're going to get at different speeds at different times. When they come back, they're going to bounce back with different intensities. And it's basically like how ultrasound works. Basically like you're getting an outline of whatever it is based on the reflections. Okay. So for every 13 microseconds of go and return time, the object creating a reflection is 1 centimeter deep in the body. Okay. So that's constant, guys. It doesn't matter. So that means if an object is 2 centimeters deep, then that's going to be 26 microseconds. Okay. That's 26 microseconds of go and return time. So if this and these are just relative numbers I'm going to use. Remember, relative is not absolute, guys. So don't hit me with no accuracy numbers. Like, that's not right. Okay, so let's set this our transducer right here, and boom, let's just say to get to this point right here, I'm gonna exaggerate, get right here and come back. That's 13 microseconds. Bounce off right there, and to get to this reflector and come back, that's double that time. Okay, that's gonna be double that time. So this is gonna be 13 microseconds, and this is going to be 26 microseconds. And this is going to continue, even though I know. So basically what I'm saying is that this point in that liver is only 1 centimeter deep. Okay? This is equivalent to 1 centimeter, because that's about sound traveling at 1.54 millimeters per microsecond. Every 13 microseconds, sound is traveling 1 centimeter. That's what I want you guys to know. That's the most important thing about this chapter. So, when we're talking about if it's 26 microseconds, take 26 microseconds, of course, that's 2 centimeters trapped. That's 2 centimeters is the depth of that reflector, right? 2 centimeters is the depth of that reflector. But that's not how long it's taking that sound to come back, right? That's not the length that sound is traveling, is what I'm saying. We're only accounting for the depth of that reflector. Okay? So if I'm talking about what is the distance that sound traveled, then I have to double the depth of that reflector, right? So it's then, because it has to go and return. So if sound is traveling, at 1 centimeter deep, if that reflector is 1 centimeter deep, then my sound has traveled a total of 2 centimeters. Okay, because it went 1 centimeter deep, it came back a centimeter. Okay, if sound is traveling at, if the reflector is at 2 centimeters, then the distance that time is traveled, that sound is traveled, is 4 centimeters. Okay, because we're going to account for the transmission time and the reception time.
Yeah.
Okay. So, since a pulse travels to a reflector and back to the transducer, the total distance that a pulse travels is twice the reflector depth. Okay. So the 13 microsecond rule applies just to how deep the reflector is. Reflector being whatever structure it is in the body. Okay. Every centimeter that sound travels is approximately 13 microseconds. Okay. The ultrasound machine is assuming that. Which is why we always have artifacts as well, because it's always assuming that it's calculating that everything is traveling at 1540 meters per second. But that's how artifacts are produced, because we know if it's fat, it's traveling at a different speed. We know if it's bone, it's traveling at a different speed. We know if it's air, it's going to scatter and travel at a different speed, right? But the ultrasound machine is not perfect, okay? But when it comes to soft tissue, it is, because it's assuming that all soft tissue is traveling at the same speed. Any questions on the 13
Is this where we increase our depth of view?
Increase your depth of.
To get that 26 from 13 to 26, so we increasing the depth of view?
Yeah, if you only have it at 1 centimeter deep.
Right, okay.
If you only have it 1 centimeter deep, definitely. but that's telling us how deep your structure is. You know, so us increasing the depth